Hello friends, welcome back in this video session of forced convection. In this video lecture, we will study flow across cylinders, sphere, tube banks. My name is Mr. S.V. Kumar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yedra, Ichalkaranchi. So, the flow across cylinder and sphere. If the characteristic length of a circular tube or sphere is its external diameter d, then the Reynolds number is calculated by the relation Re is equal to rho V d upon mu, where rho is the density of fluid, V is the velocity of that object, sphere or the velocity of that fluid, d is external diameter and mu is dynamic viscosity of fluid. The critical Reynolds number for the flow across sphere or tube is 2 into 10 raised to 5. The approaching fluid to cylinder or sphere will branch out and encircle the body, forming a boundary layer. This formation of boundary layer we had already studied in fluid mechanics subject. So, first body is a blunt body, or it is also known as bluff body. So, bluff body is that body over which any fluid flows over it. This streamline will not coincide with that body. So, here flow is separated, eddies formation starts over cylinder. If you observe carefully, so maximum pressure drag will be there over this cylindrical body and minimum skin friction, that is friction drag, is present. On the other hand, if streamline body is present, in case of streamline body, the streamline exactly coincide with your body. So, separated flow is very small, that is why the maximum skin drag is present than pressure drag. So, this is typical flow pattern over sphere and streamline body, and drag forces are shown on blunt body and streamline body. So, at a low Reynolds number, when Re is very low, the fluid completely wraps around the body. At higher Reynolds number, the fluid is too fast, means its velocity is very high. So, the fluid is too fast to remain attached to the surface as it approaches the top of the cylinder. Thus, the boundary layer detaches from the surface, forming a wake behind the body. Wake means turbulence, right? The point is called as separation point. To reduce the drag coefficient, streamline bodies are more suitable. For example, aeroplanes are in streamline bodies. Submarine, it is in aerodynamic in shape. Fish shape is also aerodynamic shape. And high speed objects all are aerodynamic in shape. When any fluid flows over cylinder or sphere, flow separation occurs generally at 80 degree for laminar flow and 140 degree for turbulent flow. And the drag force is calculated by the formula CD into A into rho into V square upon 2, where AN is frontal area, AN is its frontal area, L into D, and for sphere pi d square upon 4. So, here one example is shown, a smooth surface and a golf ball. If you observe carefully, if it is a very smooth surface, when air flows over this smooth surface, so thick wakes are formed behind this smooth surface sphere, right? Thick wakes are formed. But on the other hand, if golf ball is provided with this roughness, then what will happen? These thick waves are converted into thin wave. That is why this golf ball is provided with roughness, right? So, here this is the separation point, here is the separation point. Turbulent flow over cylinder. The case of single cylinder in cross flow is identical to the case of cooling of an electrical cable by forced convection by air flowing across it. The determination of local velocity in a flow by a hot wire anemometer, which involves the heat transfer from a single platinum wire maintained at constant temperature, and correlating the change in current to flow velocity. In order to calculate Reynolds number, the characteristic length is taken as cylinder as well as sphere as its external diameter. So, Re is equal to rho Vd upon mu or Ud upon nu, where U is the uniform velocity, d is the diameter, and nu is the kinematic viscosity. In case of flow across cylinder or sphere, critical Reynolds number, as we had discussed earlier, 2 into 10 raised to 5. Up to this value, laminar boundary layer exists, and beyond this, turbulent layer becomes dominant. Now, empirical correlation for cylinder. Whenever any fluid flows over cylinder, the empirical correlation for turbulent flow can be determined by this formula. Nu is equal to C Reynolds number raised to n Prandtl number raised to 1 by third. Nusselt number is nothing but Hd upon k or Hl upon k. But C and n values are calculated from such tables. Such tables will be provided. And how to select the value of C and n? By calculating Reynolds number. If Reynolds number is in between 0.4 to 4, the value of C is chosen as 0.989 and the value of n is 0.330. If Reynolds number falls in between 4 to 40, C value is taken as 0.911 and n value is taken as 0.385. Similarly, we have to choose the value of C and n for this relation. But Churchill and Bernstein have suggested one of the following relation as Nusselt number is equal to 0.3 plus 0.62 Reynolds number raised to 0.5 Prandtl number raised to 1 by third divided by 1 plus 0.4 divided by Prandtl number raised to 2 by 3 entire bracket raised to 0.25 into 1 plus Reynolds number divided by 28,200 raised to 5 by 8 raised to 0.8. So, this equation is valid when Reynolds number is greater than 100 and less than 10 raised to 7, and the product of Reynolds number and Prandtl number must be greater than 0.2. So, one of the relation recommended by Nakaya, that is Piclet number is equal to Reynolds number into Prandtl number less than 0.2, Nusselt number is equal to 0.8237 minus ln Piclet number raised to 0.5 raised to minus 1, and here all the properties are evaluated at mean film temperature, that is Tf is equal to Ts plus T infinity divided by 2. All liquid metal, the heat transfer relation is calculated as across the cylinder is calculated as Nu is equal to 1.125 Reynolds number into Prandtl number product raised to 0.413, and here the condition is such that Reynolds number and Prandtl number product must be greater than 1 and less than 100. For gases, generally we use Nusselt number is equal to C Re raised to n Prandtl raised to 1 by third, and all fluid properties are taken at film temperature. This equation is used for circular cylinder in cross flow. Now come to empirical correlation for sphere. So, first we will see turbulent flow over sphere. A flow of any gas over sphere, McAdams suggested one of the relation Nusselt number is equal to 0.37, Reynolds number raised to 0.6, and this equation is valid when Reynolds number is greater than 25 but less than 1 into 10 raised to 5. Here all the properties are evaluated at mean film temperature. Kramers proposed the following correlation for liquids past a sphere, that is Nusselt number is equal to 0.97 plus 0.68 Reynolds number is to 0.5 into Prandtl number raised to 0.3. But the condition is Reynolds number must be greater than 1 and less than 2000. In this equation also, all fluid properties are to be evaluated at mean film temperature, right. So, Whittaker has proposed a single equation for gases and liquids past a sphere, that is Nu is equal to 2 plus 0.4 Re raised to 1 by 2 plus 0.06 Re raised to 2 by 3 Prandtl number raised to 0.4 mu infinity upon mu s raised to 1 by 4, and the condition is that Prandtl number must be greater than 0.71 but less than 300. Reynolds number must be greater than 3.5 and must be less than 7.6 into 10 raised to 4. Mu infinity upon mu s, that ratio must be greater than 1 but must be less than 3.5. For freely flowing liquid droplets, the following Raynes and Marshall's equation can be applicable. Nusselt number is equal to 2 plus 0.6, Reynolds number raised to 1 by 2, Prandtl number raised to 1 by 3. Now, for liquid metal which flows over a sphere, we can use the following correlation as Nusselt number is equal to 2 plus 0.386, the product of Reynolds number and Prandtl number raised to 0.5. Here Reynolds number must lie in between 36,000 to 2 lakh. All fluid properties are evaluated at film temperature. Next point is tube bundle. So, tube bundles are subcomponent in shell and tube heat exchanger where flow resembles across flow at place and longitudinal flow elsewhere. You might have seen a refrigerator at your home. Now, if you observe its condenser, it is in the tube bundles. So, tube bundles or tube banks are commonly employed design element in heat exchanger. Both plain and finned tube banks are widely found, right. So, here this is tube bank but in inline arrangement, this is the tube bank in staggered arrangement. Inline arrangement means this tube is in line with this tube is in line with this. So, all the tubes are in line with each other, and when any fluid flows over this tube, heat transfer takes place between any fluid which is flowing through this and air which is flowing over this, right. In staggered flow arrangement, these are only in line but these are not in line. If you observe first and second line, these are in line here, but in this staggered arrangement this tube is not in line with this. So, it is in zigzag manner like this, zigzag manner. Some typical applications are air conditioning application, just I mentioned, the condenser of refrigeration, it is in tube bank, water tube boiler where water flows through the tube and hot gases flow across this tube. Waste heat recovery system, in waste heat recovery system again we use tube bank, and different types of heat exchanger we use tube bank for heat transfer problem. Empirical correlations for tube bank. First we will see for laminar flow. For tube bank, when Reynolds number is greater than 100, so inline tube Nusselt number is equal to 0.8, Reynolds number raised to 0.4, Prandtl number raised to 0.36, PR upon PRW raised to 0.25, and for staggered tube Nusselt number is equal to 0.9, Reynolds number raised to 0.4, Prandtl number raised to 0.36, Prandtl upon Prandtl W raised to 0.25. These equations have been validated with a range of 50 and 1000 Reynolds number. Transition regime, inline tube Nusselt number is equal to 0.27, Re raised to 0.63, Prandtl number raised to 0.36, PR upon PRW raised to 0.25, and Nusselt number is equal to 0.40, Reynolds number raised to 0.6, Prandtl number raised to 0.36 into PR upon PRW raised to 0.25. For turbulent regime, inline tube, Nusselt number is equal to 0.021, Reynolds number is to 0.84, Prandtl number raised to 0.36, Prandtl number upon PRW raised to 0.25. In case of staggered tube, Nu is equal to 0.022, Reynolds number raised to 0.84, Prandtl number raised to 0.36, PR upon PRW raised to 0.25, and condition is that Prandtl number must be greater than 1. If Prandtl number is 0.7, we can use Nusselt number is equal to 0.019, Reynolds number raised to 0.84. We can use one relation for staggered arrangement also. Nusselt number is equal to 0.0131, Reynolds number raised to 0.883, Prandtl number raised to 0.36. And this equation is valid in the range of Reynolds number from 4.5 into 10 raised to 5 to 7 into 10 raised to 6. When n, that is number of tube rows, is less than 20, then the correction factor is applied. That is, Nusselt number is equal to average Nusselt number into C, where C is the correction factor. So, for this tube bank, we conclude today's video lecture. Thank you very much.